Hello students, let's begin Lesson 6, Derivatives and Graphs. Lesson 6 has two objectives, where both of the objectives refer to the derivatives affecting the graphs of the original function. The first one is the relationship between the signs of the derivative function versus the increasing-decreasing nature of the graph of the original function. And that's a little bit easier of the two. The second objective is the increasing-decreasing nature of the derivative function and the concavity of the original function. So increasing-decreasing shows up twice, and that makes things a little bit more complicated and causes a bit of a confusion sometimes. Well, too much warning maybe. I don't want to intimidate anybody. Let's begin. Here's one. When the derivative function is positive, then the original function increases. When the derivative function is negative, then the original function decreases. If the derivative hits 0, then we get something called critical point, which we will consider a bit later. And by the way, here's a summary. Look at the first table here. The original is increasing when the derivative is positive. Original is decreasing when the derivative is negative. It's not too difficult to remember. Positive means up. Negative means going down. And that's because going up is related to positive slope. You see? Here we are looking at an increasing graph. Graph is pointed upward. Consequently, slope is positive, as you can see from this animation. Pay attention to this red line segment. That's a part of that slope of the tangent line. I mean, that's the part of this tangent line. And look at the slope. It's always positive. Pretty close to 0 sometimes, and sometimes very positive. But in any case, it's positive. Always pointed upward. Well, that's because the original graph is pointed upward. So increasing graph means positive derivative. Positive slope. Tangent line is pointed upward. You see? And vice versa. Here, graph is going down, so decreasing graph. And look at this animation. Look at the line segment. And look at the slope. Always negative. The line segment here, red line segment, is always pointed downward. So slope is negative. Sometimes close to 0, sometimes very negative, but in any case, always negative. That's because the original graph is pointed downward. It's decreasing. So basically that's it. Increasing, then positive derivative. That's because positive slope. Decreasing, that means negative derivative. That's because negative slope. And it's summarized here in the first table. Now, what if the derivative is 0? Well, we get something called critical point. Here's some examples of critical point. Here's the first example of critical point. It's a local minimum. As you can see, we have horizontal tangent. Remember, the derivative is the slope of the tangent line, and horizontal line has slope 0. So horizontal tangent means derivative 0. That means it's a critical point. Here's another example, local maximum. Again, horizontal tangent. But then again, not all critical points are either maximum or minimum, like this. It's neither maximum nor minimum, but it's a horizontal tangent anyway. Now, in some case, you're going to get some nasty situation like this. Derivative does not exist. Like this. Here, to the left, we get this slope. To the right, we get the other slopes. They are not equal, so the derivative does not exist. In that case, anything can happen. Also, this case takes place when we have the endpoint of a certain interval, like this. I mean, consider this case. Let's suppose this part does not exist. Okay? Let's suppose that I erase that part. And then pay attention to only the right-hand side. So I begin with this solid dot and look at only this part. Now the endpoint here, I don't have the derivative because I have slope only to the right-hand side. To the left-hand side, I don't have anything because, there's nothing. I erase everything here. So the end point of an interval automatically becomes a critical point because there is no derivative there. But again, these kind of situations are rather nasty, and I wouldn't worry too much about it. After all, this is 1325. We're not going to go too deeply into this. However, the other three are all very, very important. So local maximum, local minimum, or neither maximum nor minimum, you have to understand all three intimately. In any case, critical point means horizontal tangent. Let's get out of this drawing mode. And then let's go to the summary. Look at the first table. That summarizes everything. The original is increasing when the derivative is positive. Original is decreasing when the derivative is negative. And critical point when the derivative hits 0. Now let's look at the critical point in a little bit more detail. When the derivative is 0 or horizontal tangent, or derivative does not exist at all, cusp or discontinuity, then we have critical point, and we have some examples like these. Now local maximum takes place like this, increasing and hit horizontal tangent and decreasing. Graph goes up, hit the maximum, and comes down. So in terms of the sign of the derivative function, you get plus to minus. Do you see it? So right here we have critical point, and over here positive derivative, and here negative derivative. Original function changes from increasing to decreasing. That's when we have local maximum. So whenever you have critical point with transition of sign from plus to minus, you can see that this is local maximum, increasing to decreasing. See that? Now the other way around. Local minimum, decreasing, hit horizontal tangent, and increasing. Again, we have the similar deal. We have critical point here, and then we have sign change, negative to positive. Derivative is negative, so the original function is decreasing. And then hit the horizontal tangent, and then now original function is increasing. So whenever you see this transition, negative to positive, then you'll have to expect local minimum. All right, local maximum, plus to minus, local minimum, minus to plus. Now look at the other cases. In this case, plus, stay positive. Minus, stay minus. Do you see it? Here and also there. If you look at sign of the first derivative, plus, so increasing, and hit horizontal tangent, but still plus, so keeps on increasing. In this case, minus, and then hit horizontal tangent, and then if it changes to plus, then graph will go back up, so we have local minimum, but no, stay negative, so keep going down. So no sign change around the critical point. That's why we have neither maximum nor minimum. Make sense? So there you go. No sign change, plus remaining plus, or minus remaining minus, then neither maximum nor minimum. Now sign changes from minus to plus, then we have decreasing to increasing, so local minimum. Oops. And sign change from plus to minus, then we have increasing to decreasing, so we have local maximum. All those are summarized here to a certain degree. Okay, so much for the first objective, and we're going to discuss the second objective in second video here. Stay tuned.